Now let's talk about inferential statistics. We'll discuss how to generalize our sample from population, how to make sense of our findings in the sample, how to create statistic hypotheses, and how to test them. But first, we need to know some tools which are useful in inferential statistics. One of such tools is normal distribution. Normal distributions plays an extremely important role in statistics. It is a theoretical distribution as opposed to empirical distribution. Um, Empirical distribution is one that we usually find in real life. When you find a variable and you can look at the frequency of the value of the variable. So the distribution would be empirical distribution in this case. Theoretical distribution is one that are made up by statisticians. However, many variables in the real life do resemble normal distribution. So it's widely used in statistical testing and regression analysis, and it has some great properties that I will mention later. Here is how standard normal distribution look like. Probably that you have already seen it before. The standard normal distribution is a special case of normal distribution. Is the distribution that occurs when a normal random variable has a mean of 0 and a standard deviation of 1. And so that's it. The standard deviation here is 1 and the normal and the mean equals 0. So it resembles a bell curve. So you can say it looks like a bell curve. Now let's analyze the distribution. First of all, if you take a look at this curve, you can see it's symmetrical around 0. The left side of this image is the mirror reflection of the right side of this shape. The mean, median, and the mode are all 0 in this case. Tails never touch its baseline. They never becomes 0. Both tails, they never becomes 0. But they can be infinitely large or small number. However, those extreme values have very low probability of occurring. The standard normal distribution have its population mean of 0 and the population variance equals 1. There are some other normal distributions that are not standard. For example, on this slide you can see 4 normal distributions. However, only one of them is a standard normal distribution, as the blue one shows. It looks smaller than the standard normal distribution shown in the previous slides, because I changed the scale to better demonstrate other distributions. Now let's see how observations are distributed within a normal distribution. Since the distribution is symmetrical, 1/2 of the full observation lies to the left side of the center of the distribution, which is 0 here. The other half of the full observation lies to the right side of the center of the distribution. For each interval, like this, this, and this. So for each interval, of values, we can see the exact percentage of observations lie in this interval. Supposedly, we would like to see how many observations have values between 0 to 1 standard deviation from 0. So from this distribution, we know that around they are 34.13% of full observations have values between 0 to 1 standard deviation from 0. So if it's a standard normal distribution, the sigma here equals 1. So we will have 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4 here. Now let's move to standardization. Here is an example. Company XYZ sells two products A and B at non-fixed prices. Product A price ranges from $10 to $30. Product B price ranges from $12 to $45. The question is, what is a better sale? Product A for $15 or product B for $18? So depending on who you ask, we will have different answers. One answer might be that B for $18 is better than A for $15 because the price is higher. Another answer would be that, well, it totally depends on how much profits in each sale. So the question is not as easy as it might look like. The question here is that we are not clear what does the word better mean. One way to estimate whether a particular sale is good or not is to compare it to similar sales of the same product. For example, we can estimate how far the sale of product A for $15 is from the average sale of product A. So there is a process called standardization, may be used to measure a value of a variable in terms of other values of that variable, and it compares that value's variable to other values variable. There are many ways to standardize a value. One way, which is of our particular interest, is standard score, or called Z-score. A standard score indicates by how many standard deviations a value is above or below the mean. Well, when you have a particular value, what would you try to do? You would like to see how far it is from the average value in this distribution, and you try to express this difference in terms of a standard deviation. So let x be an original value of variable x. Standard score is defined as for population, standard score equals x minus the population mean and divided by the population standard deviation. And for a sample, here is the sample mean, and here S means the sample standard deviation. So these scores are very important in statistics and used frequently. What it tells us is that how large or small an individual value is relative to the average value of the distribution. So we can use these formulas to calculate the Z-score. Standard score are important for normal distribution. As previous slide shows that you can easily calculate proportions on the normal curve. So if you have an interval of values which are measured in standard deviations, you can easily calculate the number of observations falling into this particular interval. For example, if you consider an interval from -1 standard deviation to 1 standard deviation, then the proportion lies within this interval equals 68.26% of all observations. A standard score can be used to convert any normal distribution to a standard normal distribution. Why it could do so? Recall that a normal distribution is not a standard normal distribution if its mean is not 0 and the variance does not equals 1. So when we convert a value from normal distribution to its z-score, we measure this value in terms of the number of standard deviation above or below from the average of the value. So in the way that we make the mean of the value to be 0 and the standard deviation to be 1. So the z-score can convert any value of normal distribution to a value in a standard normal distribution. Since standard scores are measured in deviations, we can easily calculate proportion or percentage of values that lie below and above a standard score for a normal distributed variable. For example, if a standard score for a value x equals 1, then you can say here equals 1, then you can say around totally we add them all, add all of these percentage together, we have the number 84.13%. So we have around 84% of values are smaller than x. And around 16% of values are larger than x. Now we will take a look at the percentile. The percentile is the value of a variable below which a certain percent of observations fall. For example, we know that the center of standard normal distribution is 0. So 50% of 4 observations fall below 0. So 0 is set to mark the 50th percentile of the standard normal distribution. So in our previous example, the value of 1 marks the 84.13%, 84.13 percentile of the standard normal distribution, because the 84.13% of the variables in the standard normal distribution falls below the value of 1. And there are some tables and calculators and software that convert percentile to values and vice versa for many popular distributions. Here I give you an online calculator for you to find the percentiles. So here is the example. Company XYZ sells a product at a non-fixed price. Suppose that the sale price of the product is normally distributed with the mean of $53 and the standard deviation of $10. The question is, how does the sale price of $48 compares to other sales price? And here we can see the answer here is the value of a standard score for the price of $48 equals, use the formula here, minus 0.5. So the value of z score equals minus 0.5. Once we know this value, we can use various statistic calculators to find how many observations lie below minus 0.5 in standard normal distribution and how many observations lie above minus 0.5 in standard normal distributions. So we use the tool here to solve this question. So here basically gives you some distribution. Here we choose normal distribution, which is our interest. So here you can see the mean is 0 and the standard deviation is 1, which means this curve is a standard normal distribution. And now let's see how much observations lies below our z-score. Okay, so our z-score is minus 0.5, right? So let's see. So we can simply use mouse to get the number we want, minus 0.5. Okay, more precisely, we can use this to input the number we want, minus 0.5. Okay, so now we have the distribution like this. The red shaded area represent all the observations in a standard normal distribution that lie below the value of minus 0.5. Now we can see there are around 31% of full observation in a standard normal distribution lie below the value of minus 0.5. So we can set this value approximately the 31st percentile in the standard normal distribution. And you can also say that around 70% of full observations lies above this z-score. So using a statistical table or calculator, as I just showed you, we can find out that around 31% of all sales have price lower than $48, and around 69% of full observations have prices higher than $48. Okay, so in the previous lecture, we have talked about samples and populations. So here, just to remind you that populations are all observations that we are interested in. A sample is only a portion of population. So when you study the population, it's easy to calculate the exact value of mean and standard deviation of the population. Now suppose that it is too costly to study the full population. So you study a sample from the population instead. So what can you do with the sample? You can calculate the sample's mean and standard deviation. However, only in very rare occasions that the sample's mean and standard deviation would equal the population's mean and deviation and standard deviation. So generally speaking, the statistics from the sample is different from the statistics from population. Statisticians use sample statistics to estimate population parameters. Naturally, the value of a statistic may vary from one sample to another. So the question here is how far the sample statistics is from the population statistics. So here, standard error is used to measure the amount of variation of sample means. For example, the amount of error we can expect when we assume the sample mean to be the population mean. So standard error is how far the sample means are from the population means. So now I give you an sample. How can we estimate the standard error? There are two primary factors which can help us to estimate the standard error. The size of the sample and the standard deviation of the sample or population if known. The size of the sample. The larger the size of the sample is, the more information about the population we know, the more precise our estimation of the population mean would be. So the larger the size, the more confident that we are for that the sample mean can represent the population mean. The smaller will be the standard error. The standard deviation of the sample. Remember that the standard deviation is how much variation there is in the value in a sample. So the values in the sample are very diverse. It is probably that they are also very diverse in the whole population. This means that the value does not center the mean much. It's very difficult to get estimation of the population from the sample. As a result, the larger the standard deviation of the sample is, the less confident we are for that the mean of a sample can represent the population mean. The larger the standard error would be. Now let's look at the formulas to calculate the standard errors. Let x be a variable, then the standard error of a mean is calculated as follows. If the standard deviation for the population is known, then the standard error equals the population standard deviation divided by the square root of the size of the sample. Otherwise, it equals the sample standard deviation divided by the square root of the size of the sample. This slide brings us to the most important finding in statistics and probability theory, the central limit theorem. Different samples might produce different sample means. Therefore, we should think of a sample mean as a variable that varies from a sample to sample. In fact, standard error is the standard deviation of the sample mean variable. As any variable, the sample mean has a distribution. But what is the distribution of the sample mean variable? The central limit theorem says that for a reasonably large sample, the sample mean variable is approximately normally distributed. So remember here the rule of thumb is reasonably large sample is the 1, while the size of the sample is at least 30. These are the reasons that why this central limit theorem is so important. The statement of the central limit theorem does not depend on the distribution of the actual variable. It will be true even if the variable is not normally distributed. So knowing that the sample mean is normally distributed, we can estimate the probability of the population mean lying in a certain range of values. We can state various hypotheses and test them in a rigorous manner by estimating the significance of the test results and qualifying the probability of error. A few minutes ago, you have realized that we can view a sample mean as a variable, which varies from sample to sample, as each variable has its own distribution with its own mean and standard deviation. So the mean of distribution would be the population mean, and the standard deviation of the distribution would be the standard error. So because the sample mean is a variable, we can standardize its values. Just as we did before, we can use the standard score to standardize the value of sample mean, because the sample mean are normally distributed. So here is the formula. So when the population standard deviation sigma is known, the standard errors for sample means equals the sample mean minus the population mean and divided by the standard error calculated using the population standard deviation. So when the population standard deviation is not known, we just use the sample estimate of the standard error, so we can get the sample error. Now we have another example. Company XYZ sells a product at a non-fixed price. It's known that the average sale price of that product is $65, and the sale price standard deviation is $12. The question is how likely it is to choose a random sample of 100 sales observations with the average price being below $62. Please be noted that here we know nothing about the distribution of the population. What we only know is that this $65 is the mean of the whole population, and the $12 here is the standard deviation of the whole population. So we can, because the sample size here is 100, which is quite large, so we can use the central limit theorem and the sample means that we have learned to solve this question. The sample size is reasonably large, so therefore we can assume that the sample mean is normally distributed. So both the mean and the standard deviation of the population is known. As we just mentioned, the standard error can be calculated by using this formula. So it gives us the 1.2. Hence, the z-score for the mean of 62 equals minus 2.5. So we use this formula. So once we get the z-score for the mean of $62, we can use a statistical calculator for normal distribution to find out that how many variables lie below the value of minus 2.5. So in this case, we find that there are only 0.62% of the value lie below the value of minus 2.5 for a standard normal distribution, which means the probability of randomly selecting a sample of 100 observations with the average sale price of $62 or lower is less than 1%. So the central limit theorem tells us that if the sample size is large enough, the sample mean is distributed as a normal distribution. However, what is the case if the sample size is relatively small? If the sample size is small, the distribution of the sample mean will not be normal. However, it will resemble normal distribution and share some of its properties. In such cases, a student's t-distribution or simply just the t-distribution is used instead of the standard normal distribution. There's more than one t-distributions, each with its own number of degree of freedom. Degree of freedom are related to the sample size and the statistics that is derived from the sample. The larger the sample size is, the larger the number of degrees of freedom is, and the more t-distribution resembles the standard normal distribution. From this figure, we can see how t-distributions with different degree of freedom resemble the standard normal distribution. You may have noticed that t-distribution looks very like normal distribution, but they are relatively flatter and they also have fat tails than the standard normal distribution. So you can see here the blue one is the normal standard deviation. So you can see the other t-distributions have fat tails than that of the standard normal distribution. And also you might have noticed that as the degree of freedom increase, the t-distribution looks more like a standard normal distribution. So the yellow one has a degree of freedom of 1, but the brown one has a degree of freedom of 10. So as the degree of freedom increase, the more likely the curve looks like a standard normal distribution. The reason why t-distribution looks somewhat flatter and more spread out is that when you have the smaller sample size, you have more uncertainty about the values of the population. Therefore, the distribution are spread. The distribution is spread out. Just as we calculate the z-score for sample means when the sample is large, we can also calculate the t-score for sample means when the sample size is smaller. The formula is exactly the same as that of the z-score. The only difference here is that the value of t-score is not related to standard normal distribution, but to a t-distribution. The t-distribution varies with the parameter, which is the degree of freedom as we mentioned. So if the sample size is n, then t-scores for the sample are associated with t-distribution with n-1 degree of freedom. So when you have a value of t-score, we can check the statistic table, which describe the t-distribution with n-1 degree of freedom, while n is the sample size, to see how many observations lie below the particular value of the t-score and how many observations lie above this particular value of the t-score. Now let's take a look at another example about how to use the t-score and the t-distribution. So again, we know nothing about the distribution of the monthly product returns of the product X, because this company ABC believes that the average number of monthly product returns of a product X should be equal to 20. However, for the last 6 months, the average number of monthly product returns was 25, with a standard deviation of 5. So again, we know nothing about the distribution of the monthly product returns of product X. The question is, assuming that the company ABC's estimate of having 20 product returns each month on average is correct, how unusual is the number of the product average returns of 25 in the last 6 months? So in this case, we only know that the population mean equals 20. And we also know that we have a sample of 6. We have sample of 6 observations, which is not large. The mean of sample equals 25, and the standard deviation of the sample is 5. So that's all we already know. The sample size here is quite small, only 6. So in this case, we should use t-distribution instead of normal distribution. So here we have the answer like this. The population mean is 20 and the population standard deviation is not known. However, we know the sample standard deviation, so we can use the formula we learned before to calculate the standard error. Use this formula, so we get the standard error of 2.04. The t-score for the mean of 25 can be calculated using the z-score formula we mentioned in previous slides, which gives us 2.45. The sample size is 6, and the calculated t-score is related to t-distribution with 6 minus 1, which is 5 degrees of freedom. So using a statistical calculator, we find that approximately 97% of values lie below 2.45 in t-distribution with 5 degrees of freedom, and only 3% of observation lie above 2.45. Therefore, the mean product returns of 25 is unusually high. The company may want to further investigate this issue.